Hello everybody, my name is Stephen Goldfarb. I am a particle physicist and I work at CERN, the European Laboratory for Particle Physics, here in Geneva. I'm going to give you a little talk here about a subject that interests me. It's about particle physics. I'm going to talk to you a bit about the Large Hadron Collider, which you might have heard of. And I want to start out by discussing how we measure what we can't see. This is a physics seminar. Well, they're not usually this packed, but this was one that was given on the 4th of July in 2012. It was a very technical seminar. There were lots and lots of plots. The physicist presenting from the CMS experiment at CERN had, if you look very carefully up there, you'll see this is his 106th slide. So there were many slides in the presentation. The presentation from the ATLAS experiments, or both ATLAS and CMS, these two experiments they presented, gave its climactic result here, which caused everybody to celebrate because it had this number 5 times sigma, a Greek letter, 5 sigma, and that got us very excited. The next day, the newspapers, the magazines, the news shows were filled with images of this big event, and over the course of the week, 1 billion people, that's a lot of people, saw video from that presentation. Why? Why were we so excited about a scientific seminar? Well, if you go back in time a little bit, there was a previous seminar. It took place also on the 4th of July, but it was a lot earlier. And here you can see the seminar which is being given by a brilliant physicist by the name of Og. She was presenting to her colleagues some results that were found, of course, by her students. Students always do all the work. Zog had discovered that if you smashed things together, you could learn about them. He smashed rocks together and he found out that rocks were made up of smaller rocks, which was, it was groundbreaking at the time, but fascinating. It turns out that human beings, since the beginning of time, have a lot of really big questions, very basic questions. We look around and we ask these questions to ourselves. Where do we come from? What are we made out of? What's our destiny? What's going to happen to us in the end? And what are the rules behind all of this? And finally, is there anything else out there that we don't see? Now, we have some tools that we've used throughout history to try to make measurements, to try to understand our universe. This is one of them. This is an extremely precise and wonderful tool. It's very versatile, and it has been what we've used for hundreds of thousands of years to do scientific measurements. That tool can measure human hair. It can measure to tens of microns. You can see my friend Eva's hair here. Beautiful blonde hair. That hair, one of those strands, is tens of microns. Our eye can see that. That's very high precision. We can also look way out into the distance. We can see 2.5 million light years away to the next galaxy, Andromeda. If you take a look, it's right there. A bare eye can see that. You don't need a telescope to see that. Pretty amazing what we've got. So that's great, right? That's enough. I mean, with this thing, we can do everything we want to in science. Well, no. We're human beings, and we're never happy. We want to see more. As a physicist, I have a lot of fun because I like to show off what we're doing. This was a virtual visit I did with some students who were in a place called Seward, Alaska. And we were discussing, this is my friend Dave Barney, he's from the CMS experiment, I work on the ATLAS experiment. We were talking to them, we were in front of our control room, and they asked this great question. I think it's the young boy there wearing the Netflix and chill t-shirt. And he asked this question: how do we measure what we can't see? Of course, students ask the best questions. There is no doubt about this. This question is at the heart of science. That is science. How do we measure what we can't see? Well, there's different ways that we do that. We do that by exploring, building devices that allow us to see more, like microscopes, telescopes, or traveling to places that are far away, so we can see things we've never seen before. We also do it by what I call extrapolation, thinking about things. Based on what we've seen, what do we know? We see that this bright orb keeps coming up every morning, and we can extrapolate and say, maybe we're on a round planet that's turning, and we're seeing the sun each time anew every day. In fact, we knew about this a long time ago. Several thousand years ago, a man named Eratosthenes didn't just know that our planet was round, but he measured the circumference. He was able to, by putting a post in the land, measuring the shadow, knowing where the sun was straight up and down, he could measure the circumference of our planet within a few percent. He knew what the circumference of our planet was. So we're able to not just look at things, but also from that information come up with ideas. In experimental science these days, this is called experiment and theory, are what these two things are. When we look out, what have we learned? Well, over time we've learned a lot of things. This guy named Galileo, you might have heard of, he came up with this idea of using glass to build a telescope and to look out into space. He was able to take this nice image, he didn't take a picture at the time, but this is what he could see. Jupiter has moons around it. You can almost do this with your iPhone now, okay? Now you can do that. The good camera, you can take a look out there and you can actually see that there are moons around Jupiter. Over time, we built better and better telescopes. We took them and put them out into space. When we put them into space, they got above our atmosphere, and then we could see far out into the distance. This is the Hubble telescope. There are other ones out there. There's many beautiful telescopes out there looking all around for different things. And we found out that there are many, 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 many stars out there. We also listen out. Most recently, there's an experiment, the fantastic experiment called the LIGO experiment, and also the Virgo experiment is similar to this. And they are designed in a way that they can detect if these long components on them, these long rows there, which have laser beams in them and mirrors, they can detect if they change size within less than the size of an atom. They can detect that. They can see that. And by doing that, they can actually measure whether space-time itself has changed. And that can happen if something enormous happened way back in time. For example, two large black holes merging. Some massive event like that could cause space-time itself to ripple. This was just found out that this works a few years back, and now they've made many measurements of various things happening. It's just an amazing experiment. So we not only look out, but we listen out at what's going on out there. We also look in. We developed a nice machine here with a little thing called a microscope. We use that to look at things like Eva's hair. Here you can see her hair up close, and you can see what it's made out of. We built even better things. We found out that if you use other types of particles like electrons instead of photons, so if you use higher energy, you can go to smaller distances. And here you can see, well, that's a thing that was not on Eva's hair, but it itself has hair. You can see an ant in all of its detail. Isn't it? It's amazing the detail we can see with an electron microscope. But we can do even better than that. If we take particles at even higher energy, we can probe to even smaller distances, and you can see and measure different types of particles. You can see what we're made out of, answering one of those most important questions. What are we made out of? And this is something that we've been doing here at CERN. This is an older photograph. This is a bubble chamber. We've advanced our detector technology since then, but this is similar to what we're doing now. So what have we learned with all these nice devices? Well, we've learned that we're on a beautiful blue, fragile planet that is one out of several planets, 8 or 9, depends. I like Pluto myself. Planets surrounding our star. And our star, our nice warm star, is just one of 100 billion in a galaxy. And that there are probably around 100 billion galaxies in the universe. We're insignificant. It's great. It's fantastic. There's just so many other things out there. And we've learned not only about what's out there in space, but we've learned a bit about time. When we look out at the light that comes from way far away, it takes time to get to us. And at that time, we can measure the further ones that we look at are older. And so we have figured out exactly how our universe expanded over the course of time. We know that we're about 13.8 billion years old. And I don't feel a day over 10 billion, to tell you the truth. When we look in, we learned about Eva's hair. We learned that it's made out of cells, that cells have molecules, molecules have atoms. Inside atoms, there are nuclei, and inside those nuclei, there are things called protons and neutrons, and we've gone beyond that. We've found that protons and neutrons are made up of things called quarks. We found that there's even more fundamental particles. Right now, this plot in the middle there, the U, C, T, G, D, S, P, you see that those are what we think are the most fundamental particles. Those particles are not made up of anything. That's it. We could be wrong. We've been wrong in the past. We thought atoms were it. But all of our measurements up to now indicate that these are it. These are the Lego bricks that we're made out of. This is it. Those particles. I've plotted it here in the order of their mass, the mass of those particles, which we have been measuring. The coffee cup on the right tells you the rules that we've figured out of how they interact. What are the rules behind all this? From our measurements, we've come up with a set of rules which explain how those particles interact. We've come a long way. But you ask me, you say, Steve, mass? Why do you say mass? What are you talking about mass? How do all these different fundamental particles have mass? They aren't made up of anything. How can they have mass? Well, that was an important question, and this guy, Peter Higgs, along with others, Francois Englert, Robert Brute, thought about this way back in the 1960s. They were thinking about this because they found out that there were some of these particles had to have a relatively large mass in order for them to make the calculations that matched what we measured. This was really puzzling. How did fundamental particles have mass? They came up with an idea. They said that there's this mechanism, there's actually a field that's everywhere in the universe that appeared just after the Big Bang, and that when fundamental particles interact with that field, they get mass. The amount that they interact with the field tells us how much mass they have, or how much mass they have tells us how much they interact with the field. Same thing. This is what they proposed. To figure that out, whether that was true or not, we needed to measure and find that field. They told us, forget about it. You're never going to do it because it's hardly, the particles would be really, really hard to find. It'd be really rare for you to find them. So we decided to look for them because that's what human beings do. We built many accelerators trying to find them. The most recent was a Large Hadron Collider at CERN. This is what it looks like down inside the tunnel before we had everything closed up and finished. This is what it would look like if you could see it from up above. You can see off to the right there's the airport and there's the lake which comes down to Geneva. There, it's called Lac Léman, and over to the left there's some mountains called the Jura. That's where Jurassic comes from. They found fossils on there from the Jurassic period. Under there there's this round accelerator called the LHC, the Large Hadron Collider. It's 27 kilometers around, and at 4 places along that accelerator we bring protons right through each other, and we measure what happens. The way we measure what happens is we build these detectors. So these detectors, CMS, LHCb, ALICE, and ATLAS, these are 4 beautiful, incredibly large and complex devices which are designed to take pictures when the particles pass through each other. 40 billion times a second they're doing that. And we're detecting and we're measuring that. Amazing, amazing thing. Here's what we found. We did it. After all of that time, almost 50 years later, in 2012, it's actually 48 years later, the ATLAS and CMS experiments made the discovery. They found the Higgs boson, which is the particle which makes up that field. Okay, and that was the culmination of all of this. We got very, very excited, and now you understand why we were so excited in that picture. we celebrated the following year with Nobel Prizes for Francois Englert and Peter Higgs. I'm going to tell you more about the Higgs boson later on, but I think that's something that's worth celebrating, that we were able to find an almost impossible thing by looking at what we can't see. Thank you.